Hi, everyone. I'm just going to talk about a presentation on graph neural networks, something that I've been working on quite a lot recently, and something that has intrigued me for a long time with regards to what it can do and what are the approaches, what can be done with it, what it has solved already, and how it mainly works. So I just want to more focus on the architecture and what happens when training is done, and what happens and how we can use it to solve some applications. So basically, a graph neural network starts from a molecule first. So you can think of an example molecule with we have atoms and bonds, and their coordinate system in 2D plane, or it could be 3D, depending on what is given from an application that we have. The first step is to convert this molecule into a graph format using a concept from graph theory in computing science. What happens mainly is all the hydrogen atoms are labeled where they are, and all the carbon atoms or all the different kind of atoms are labeled with node and edge. With what we call here is a node. A node represents an atom, which can have a symbol. It can have other features like valency or weights or any other atomic specific features. And different nodes can have different symbols. We can represent different atom types with different nodes. The edges, in terms of the graph theory explanation, is a chemical bond between two different atoms. Edges can be a single bond or double bond, depending on what it is, and an edge can have more than one information, not just what kind of bond it is and what is the distance between two atoms in that bond, and any other edge-related information, quantum specific might be. But in essence, what's happening first is we convert a molecule from chemistry representation into a computational representation using graph theory, by using node labeling for atoms, and for bonds, we define them as edges. So the next step would be, how can we featureize a graph? So first step was from molecule to a graph format in computational terms. And the other step, after we convert the molecule into a graph format, we can create a table. A table, like we can label each and every atom here. Say, for example, here we have a carbon atom that we can label, for example, here. We can assign a node index. We can also assign XYZ in that 3D coordinate system. If it's a 3D molecule, we can have these values together, and other features like molecular weight or valency or any specific atomic features that we can have. So we can make a table out of it in computational terms when we try to analyze that. And after making a table of nodes and atoms, we can go forward to making a table of edges. For example, here we can make a list of edge types, bond types, which could be single, double. And age is basically a connection between two nodes or two atoms. Here, in case because all the nodes are indexed by numbers like 0, 1, 2, 3, 4, we can in a computer program we can connect two different atoms together by having an array of indexes, node index. 0 and 1 represents an edge between the 0th carbon atom with the first hydrogen atom, and then we can also have other features of these bonds, like what is the distance in the 3D geometry in a bond. We can add features like that, and why it's important, because we want to understand how this molecule is represented in a graphical format, and what are the features and what are the properties of this graph, what are the properties of the atoms and edges, and we try to model each molecules in terms of nodes and edges, with features for every nodes and every edges. Just a brief review of why we are doing this, because we want to combine this graph that we collected features and data for, and we want to combine this data into an ML task by starting with the molecular data, nodes and edges features as an input, and then we can have a model that processes this input in some way, trains them, learns them, and at the end it creates predictions. and that could be task specific depending on what we want to do. There's possibility of learning molecules to predict their toxicity, admit predictions, and all kind of different applications that can come with it, predicting molecular weight, predicting solubility. So we can do all kinds of different applications just by understanding or modeling a molecule in a graphical format and using the features, encoding the features, and using an ML algorithm downstream to solve these tasks. So here's where the concept of graph neural comes, is a graph neural network is a combination of a graph theory and ML on molecular graphs. So we start with the graph theory. We represent entities as nodes, atoms as nodes, and the relationships as edges. The idea is to capture these relationships and encode information in a graph. It takes concept from molecular structures where molecules naturally fit into graphs because molecules are a group of atoms that are connected with bonds and edges. And then with these two ideas, we can combine machine learning theory idea, which leverages features like node features and edge features to predict labels like toxicity or other admit prediction, drug toxicity, things like that. And there is where GNN combines these three concepts together to solve ML problems from molecular structures, learn from both node features like atomic number, valency, weights, and edge features, which can be bond type, one hot encoded can be, or distance between two atoms, all this information we can encode together to learn from them and solve a downstream task like toxicity. So this is in a brief review of what happens inside a graph neural network, what is the process and what it has. So I just wanted to have a summary of, before diving deeper into it, what it has. So initially, it's something called a node feature aggregation, where all the nodes gather initial features from their own attributes. So node features could be weights, valency, atom type, XYZ coordinates in that molecule. After that, what it does is something called message passing, which is where nodes exchange information with neighboring nodes. So these features of these nodes are exchanged between other nodes that are connected to each other, and this is how they pass messages. After passing messages, each of these features will be updated with these messages so that nodes are aware of their neighbors. We want to capture the spatial relationship and combined relationship between atoms and how they interact with each other in that spatial coordinate system. So that's why the feature update is an important step. And after the feature update is done, we use these features to do predictions downstream, which could be regression, classification, like predicting toxicity, or could be predicting atomic specific properties. So I just wanna describe what's happening inside a graph and what are the different steps are. So initially, we can think of this molecule as a graph of 4 different nodes or 4 different atoms, which are labeled 1, 2, 3, 4. We can think of them like as carbon, hydrogen, oxygen. And each of these nodes has features, say x1, x2, x3. And each of these nodes will have different features because they're different atoms. And their XYZ is also different. Maybe there are other features that can be used to represent these atoms in the graphical format. So initially, we have all this, 4 different atoms with weights initialized and their features initialized. What happens in the next step is aggregate function. So what happens here is defined by these arrows here. And we can look at these arrows. What's happening is if we take the example of the first bond or the first atom here, number 1, which are represented by the blue features, what's happening is it gathers information from 2 and 3, which is connected with, because 1 is connected to 2 and 3. So this is where the message passing happens and aggregation happens, is these features are shared or exchanged with whatever it's connected with. And after the features are shared, what we call an update happens. An update is basically we update the node number 1 feature with information from node 2 and node 3. And we can see that things have changed. After the update happens, the blue color is not there anymore. So we have, for the first node, we have different colors like blue, yellow, which means that it has used information from its neighbor nodes. to update its own features. After the update happens is then we update features for all different nodes, not just for one, also for 2, 4, and 3. So all the nodes in the graph will have updated information from its neighboring nodes, and their features will change, which is what we call downstream. Their features will change because they have shared information about their spatial features with each other. So that's happened in the first step. What happens in if we have multiple layers of this neural network, what happens is it can share this information multiple times with different nodes, and we can iterate this process over and over again to share information multiple times. And after multiple updates, what happens is the immediate neighbor will share information with the neighbor of a neighbor. The message is kind of passed from 4 to 3, 4 to 2 to 1, and the information will be exchanged if we do it multiple times. It depends whether we want to do it. It depends how you encode the GNN and what it's supposed to do. Maybe you'll have only one layer and you don't want information to be passed from one atom to a far-reaching atom. So that means you might want to reduce the number of iterations you do. But if you do want that information traveling between one node and another node far away, then you might want to do multiple iterations and share information between different nodes. The target is to capture their relationships together, not just look at one atom with itself, but look at it as a relationship between different kinds of atoms and share information between each other. So after this happens, I just want to have a GIF here, which I collected from the internet. This is kind of what happens in a GNN in layer 1. You can see that everything is initialized with 0 values. Those are what we call embeddings. And then when sharing happens is for each and every one of these nodes, they share values between each other, node features between each other, and update these nodes together. And after this updates is done over multiple layers, then we can go to a point where information is shared between each and every nodes, and we can be able to predict something downstream after that. These are some of the aggregate functions that we use in graph neural networks. Is we can sum or mean or max. What it means is summation is basically for every node, it would sum all the features of its connected nodes together and update that. That means summing all the features for its neighbors and then updating that value. It can be a mean as well, which means basically for every feature, we would calculate the average of all the features of its neighbors and then update that value. There's also other aggregation functions called max, which is just taking the maximum feature value of its neighbors and updating that. And we can think of it as conceptually similar to pooling layers in CNN, where we have kernels that does max pooling, average pooling, and summation pooling is also done. I think in terms of GNN, summation has been a better aggregation functions, but it really depends on the application that you are, and it's very specific. It could be very specific to an application that you're trying to solve or the particular structure that you're trying to learn. And there are also customized aggregation functions as well, but those are like very specific to different problems. So in summary, this is kind of basically what's happening inside a graph neural network is it starts with a node aggregation on the right. It receives features. It has neighbor influence, and then it does message passing, which is basically sending features of each node to its neighbors. And it can receive messages as well for every node. After that, a feature update is happening where it combines all these messages together to update nodes, to update the features of each and every node. So that the spatial information is collected, so that we can capture the relationships between different atoms, how they're connected to bonds as well. And after the node update is done, feature updates are done, we go forward to do some prediction, which can be classifying nodes, classifying atoms with different features, could be predicting edges or predicting edge features as well. It could be labeling graphs. Labeling graphs could just means that it's predicting toxicity or doing classification or regression on the entire graph itself. So basically, the key ideas of the GNN is this idea of iterative process of message passing that enables the GNN to learn global graph level representations from local structures. Basically, meaning it would learn how a molecule is represented on a graphical level, and what are the relationships between atoms are, whether information is passed or not, how one atom influences the other atom in a molecular level. Closer neighbors will have larger influence from further neighbors is because initially it looks at each node and its neighbors, the ones that are connected with bonds, the ones that are connected with edges, first to update the nodes themselves. So closer neighbors will always have a further influence. But once you have multiple message passing layers, if you iterate multiple times, then that influence is reduced, which can average out these values. So think of message passing as graph level convolutions as well. If anybody has worked on CNN deeply, they know that there are convolutions in CNN where the kernel applies transformations on the image features and does some calculations. But message passing is a very similar operation, except that it's done on a graph level with nodes and edges. It can be similar operations as well, like maximizing, summation, on averaging. This is how a kernel updates its embeddings as well. Node level embeddings are learned by feature aggregation. We learn node level embeddings, which are the weights of a neural network. And this can be learned as a result of backpropagation, which works like any neural network. Is when we update these weights after doing prediction, forward propagation. We learn the loss and we'd update each weights with the loss that's learned so that the loss is minimized in a backpropagation network. One key usefulness of GNN could be it can be rotationally and translationally invariant, which means that if you rotate the molecule, translate the molecule, make it larger or smaller, it should still know what it has learned. And that can be made to be like that. It's not always like that, but you can create the structure like that. But it's very unlike a CNN where if you rotate the image or change the structure of the image, it would need to be relearned again because CNN is kind of grid. It's not represented in a graph. It's kind of a grid-like structure, and it does not learn rotational or translational variants easily. And obviously, with every neural networks, there are challenges to learning, and there are pitfalls to it. There are advantages as well and disadvantages as well. The disadvantage of GNN, where the challenge comes, it's a very highly computational cost for large graphs, both in terms of time and space complexity. This means that if they're like for small molecules, it's not computationally costly, but for large molecules like proteins or even DNA strands, that would be really, really difficult to calculate because updating nodes, updating atoms and edges will take a really long time. And that would make it computationally very costly to learn or to be used in terms of large genomes or proteins even. That's why it's very specialized for small molecules or large molecules, but on a molecular level. It's also not scalable to large and fully connected graphs, which means that if every atom is connected to every atom, a fully connected graph, it would be also take a long time to learn because it has high time and space complexity. But that again makes it ideal for small molecules or other kind of molecules because in the molecule, atoms are not connected to every other atom. It's usually it passes by bonds. There are bonds, so that's why it's easier to handle that way. Because in a molecule, generally we don't deal with fully connected graphs. Somehow lightly connected, each atom will pass information from one to another down the road. Another problem could happen is if there are too many message passing layers, which means if there are too many iterations of updates, this can lead to oversmoothing where node embeddings are indistinguishable across graphs. This happens when you're like averaging multiple times over each and every node. What happens is these values will become very similar over time. They would converge to the same value, and it would not be possible to learn whether one node is different from another node or whether one atom is different from another atom if we do the averaging multiple times over multiple layers. And some of the applications, it's just a picture that I took from the internet, is we can think of node prediction as in predicting a value from an atom. And this can be applied to multiple different nodes. There's ways to selectively predict nodes. Say we want to only predict properties of hydrogen atoms, not carbon atoms. That can be done as well. That's difficult in a CNN, but in graph neural network that can be done as well. We don't want to predict properties for every node. That can be done. We can predict links as well, which is edges or bonds. What are the one of the link predictions could be J coupling prediction, where we predict J couplings between two different hydrogen atoms. And another application could be understanding or learning the entire graph to predict toxicity, for example, ADMET prediction, solubility, molecular weight, all this kind of downstream applications can be done over the whole graph itself. So that it just gives out or predicts one value, could be real value or a label like toxicity. Other applications here discuss about the node regression, where one example is NMR chemical shift prediction, and the best state-of-the-art models are actually graph neural networks that can model the chemistry really well. There's specific architectures that have been designed for it to work well, for example, SHNet. And the state-of-the-art models are actually graph neural networks that can capture the relationship of between different atoms in an NMR experiment. One example of an edge regression is J-coupled prediction, which is basically predicting J couplings between different atoms, like hydrogen atoms, and then predicting that. There has not been too much work on J coupling prediction using graph neural networks, but this could be an avenue of research that someone can take on and see if there is really a great model out there that one can build to GNN and that can do really well on J coupling. Then there's molecular labeling itself, which just gives out one value for each molecule. So it could be toxicity or ADMET prediction in terms of drugs. And recently it has been used heavily. It is actually a core component of AlphaFold 3 in predicting protein structures, where protein residues are given XYZ coordinate, and the target of GNNs inside AlphaFold 3 is to predict where in the spatial coordinate system does that protein reside, like mainly predicting XYZ in protein structures. You can also build hybrid structures architecture with GNN, and that has been done recently as well, quite studied extensively. With GNNs have been combined with attention mechanisms, which is a key component of LLMs. And using this attention mechanism, we can create something called graph attention networks that can leverage attention layers and build or learn relationships between atoms, which cannot be learned by typical graph neural network. This has been done, and then there are some studies that demonstrate that graph attention networks are better in that particular problem compared to regular GNNs. There's also recent studies where recent papers that have been released, very new, where they have combined LLMs, which basically they have encoded smiles in some kind of BART model to represent structures, and also modeled a 2D structures together to give multiple different features, and they fed it to an LLM. The paper is named Molex, and it has kind of beat the state of the art in a few, I think, property prediction, molecular property prediction. But these are the ideas that demonstrate the usefulness and how you can combine it with other architectures together to solve different kind of downstream problems. It's important to have hybrid architectures. It's just because how in the field of multiomics, you need to use sometimes protein structures, small molecule structures, genome structures, and these are different and very different in terms of features as well. So it's sometimes important to model them differently. Small molecules are generally modeled with GNN, and maybe protein sequences are modeled with LLMs. Those are better in terms of that. So they have all pros and cons, but I think it's important for a particular application to study what can benefit what. It might be that GNNs are not useful in some applications. LLMs are better useful. It can be the other way, but I think there's a lot of research that needs to be done in ML and GNN to understand whether we can create better architectures or better models to model different kind of problems. Yeah, thanks for listening to my presentation. I've added a few references if anyone wants to check it out. Yeah, some papers as well. I can share that to the group. Thank you.
Great. Thanks.